iOS developers. I wanted to use this Sunday to create a video about suspension points in Swift. And let's get straight into it. Here I have some code set up which we'll use to understand what suspension points are. We'll also go a bit further into it and talk about how to manually suspend your code. That will come later on. So what is a suspension point? A suspension point is a place in an asynchronous method which calls another asynchronous method. So in this original method here, we're calling out to another asynchronous method. And it is here that we are experiencing what we call a suspension point. And while calling this other method, the original method gets suspended, hence the name suspension point, or in other terms, paused, until the other asynchronous method finishes. When the other method finishes, the original method continues executing its code after the suspension point. And suspension points are at the core of async await. While the method is suspended, its thread does not get blocked. Rather, it is freed up for use. This freeing up of the thread is the most important part of suspension points, and it is what actually makes the method asynchronous. Without the suspension and subsequent freeing up of the thread, the method would behave just like a regular synchronous method. That is, it would block the thread while another potentially long-running method or task gets executed. And when the method is continued, it might continue on a different thread than the one it was on previous to the suspension. So for example, if we were to print the current thread before the suspension point and the current thread after the suspension point, we can see down here that those two threads indeed are different. This means that we shouldn't really make any assumptions about which thread the code gets executed on after the suspension point. And in general, you shouldn't really care about which thread the different executions are run on. That is abstracted away on purpose. However, there is one exception. If you need to perform work on the UI, you have to force the execution back on the main UI thread. So this is something that you also need to keep in mind. If you create an asynchronous method that sometimes suspends and sometimes doesn't, the caller of the asynchronous method always needs to await explicitly, like we're doing here with the original method. And what do I mean by potentially sometimes suspending and sometimes not suspending? Well, I'll show you an example here. If we say call the method potential suspension point, we make it asynchronous, and we do an if-else statement in here. So we say if bool.random and else here. In the bool.random, or in the true case, let's actually call out to the other asynchronous method. And let's also print other here. In the else case, let's print, or actually let's not print other, let's print suspended, and down here let's print not suspended, like so. Now we'll call out to this potential suspension point. So what we see here is that in the true case, the method or the task on which the method is run on actually does get suspended, while in the else case it does not get suspended. And even though it sometimes suspends and sometimes doesn't, we still have to mark the call site with the await, and thereby explicitly awaiting the potential suspension point. And that is why people often refer to suspension points as potential suspension points, because you don't really know how the method underneath is implemented and whether or not it will always suspend or just sometimes suspend. And even though we have all these suspension points in our code or in our Swift program, there are still ways to actually block the thread. And I will show you how this might happen and also show you how we can mitigate this problem. So let's first remove all of this here, and let's, for example, call out to a function that we'll call long running task, like so. Make this synchronous, and for now let's just loop from 0 to 100, and let's also print finished here. Now let's await the long running task and just run our program to see that everything works as it should. We see that it finished indeed, but if now we were to go from 0 to 100 million, we will see that when we run the program, it won't actually be able to finish. And that is because the long running task takes more than 5 seconds to finish, which means that it won't have the time to execute. Now let's create another task here, and let's just print other task, like so. Let's run this again, and as expected, this other task gets the chance to execute. Now let's look at what would happen if we were to run a huge number of long-running tasks in our system and how our program would behave. So let's say we have 1,000 long-running tasks created. So let's move this into the for loop, and let's now run our program. So we see now that the other task does not get the chance to execute. And what is actually going on here? So what is going on is that these long-running tasks are assigned a particular thread on which they're doing their execution on. And since each of these long-running tasks are indeed quite long-running, then the thread gets occupied until it finishes. And since we have created a huge number of long-running tasks, all of our threads in the system are getting occupied, which means that this task down here does not get a thread on which it can execute its code. So how do we actually mitigate this and allow for this task to jump in and do some work in between these long-running tasks? Well, Swift gives us a tool that is called task.yield. And with this task.yield, we can actually manually suspend the task on which we are running the current execution on. And of course, the compiler says that we have to await because this is an asynchronous method. So we could implement this by saying, for example, for every 100,000 number, we would yield the current task. So for example, if the number is multiple of 100,000, then we yield the current task, which in essence mean we are suspending the current task and allowing the thread to be freed up again. And since we are allowing the thread to get freed up, it means that in theory, this other task should be able to jump in on a thread and do some work. So let's try and see if this actually is the case. And indeed, we can see down here that the other task does actually get the chance to jump in and do some work, even though we have quite a few long-running tasks executing. So hopefully you found this video educational, and I'll leave some resources down below in the description on suspension points and also async await in general in Swift. Thank you very much for watching, and see you next time.